So the x center of mass is easy. It's going to be 0 because of symmetry. Y center of mass, we start with the equation 1 over m integral y dm, where we take a horizontal slice, and the x position is actually only half of the entire rectangular slice. So I'm going to start actually with density in order to replace that dm. So the total mass of the semicircle is equal to the area of the semicircle, which is half of pi r squared times the thickness of the plate, whatever that is. And it's only half of pi r squared because it's only a semicircle instead of a whole circle. And that equals dm over, and then my little sliver has a length of 2x because it has to be the whole rectangle times the thickness of the plate, which is the same as on the other side of the equation, and then times dy, which is the little vertical thickness that we have. Okay, so then just do some rearranging to get dm by itself, and I'm going to substitute that in up here into the other equation. You can pause the video as you need in order to figure out where things went. But what I'm going to do is I'm going to simplify this a little bit, pull my constants out front. The problem with this equation is that I can't take the integral of x dy. I need to find an equation for x equals to something in terms of y. And so I'm actually going to use the fact that we have a little right triangle there. And the x squared plus y squared then has to equal r squared by the Pythagorean theorem. And then rearrange that to find x in terms of y. Great. Now I can take that and plug it back in to this equation. So we have the y center mass equals our integral. Now we're going to integrate from 0, which is at the x-axis, up to the highest point, which is at r. And then this integral becomes y times, because the y is still there, x, which is now square root r squared minus y squared. And then, of course, with respect to y. This is not an easy integral to do. So what we need to do, remember in calculus we do this crazy thing called a u substitution. So we're going to substitute this r squared minus y squared for u, like we're going to just call it u. And I'm going to find du dy so that I can then substitute into dy. So du dy is equal to, well, the derivative of that function is just negative 2y. So y dy, I just moved the dy to the other side, is equal to du over 2, and it's still negative. And so we're going to take that and plug that back into our equation. So here's our integral that we had earlier. But then instead of square root r squared minus y squared, we're going to replace it with the square root of u. And then the pieces that we have left, this y and dy, those are going to get replaced with negative du over 2. And now it's an equation that I can integrate. So I just simply rewrote it. I pulled the 1/2 out front and the negative. And then I have my integral. And then it's u to the 1/2, which is easier for me to integrate than a square root. So then that becomes the constants out front times 2/3 u to the 3/2. And then I'm going to evaluate that. I'm going to plug my square root, or my r squared minus y squared, back in for u. So I just simply replace that. I don't know if you can see, but the negative 2 times 2 becomes 4. And then on the bottom, we have the 3 pi r squared. But then instead of u to the 3/2, I have r squared minus y squared to the 3/2. And I then just rewrote it with the square root in there. And then I'm going to evaluate that from 0 to r. And so constants stay out front. I'm going to plug in r. So I'm going to have r squared minus r squared to the 3rd minus, and I'm going to plug in 0. So that'll be r squared minus 0 squared to the 3rd. And then the constants stay out front. This is going to get reduced to negative root r to the 6th, because of course the first piece becomes 0 minus square root, and then it's r squared to the 3rd, which is r to the 6th. And so then that becomes r to the 3rd, and you have a negative times a negative, which becomes a positive. Oh my goodness, it's almost there. So y center mass equals 4r over 3 pi, and we got it. Phew.